Qualitative and quantitative analysis. So qualitative analysis is a technique or a practice or a process that's used to determine if an element is present in a given material. It can also be used to determine if there's a particular ion in a given material. For example, gas tests can be used to determine the presence of gases. So, if you test for oxygen gas, you do the glowing splint test. If it relights, it's oxygen. Hydrogen gas is present, the burning splint pops. You can do precipitation reactions where you add a specific, you choose it wisely, solution to your sample, and based on whether or not there's a precipitate and what color it is, you can determine if a particular ion was present. And there are some very nice flowcharts and graphic designs for determining how to figure that out. And colors of solutions or flame tests can also be used to determine if something is present. For example, a blue solution could indicate that you have copper 2+ ions present. Another neat way is the flame tests. Flame tests. You can put a sample of your compound or your solution into the hottest part of a Bunsen burner, and you will see a color above the contact point, and based on the color you can identify your elements. So this is a really nice chart of flame test colors put out by a gentleman who's a teacher in England, and he does all kinds of beautiful infographics for biology, chemistry, common stuff in our everyday life. You should really check him out. Quantitative analysis, then, is a process to determine how much of a substance is present or how much product theoretically can be produced in a reaction. A great deal of chemistry takes place in aqueous solutions for a number of reasons. Water's cheap, readily available. It dissolves many substances. It's known as the universal solvent. Faster reactions will occur because chemicals can mix more completely when they're dissolved. When there's ions floating around in solution, there's greater contact. It's easier to control reaction speeds by adjusting the temperature or reactant concentrations. Being able to predict the quantity of product or quantity of reactant required is critical for the success of chemical processes. For example, water treatment. You need to know how much of a treatment to add for your problem. Add too little and you don't get rid of your problem. Add too much, you've got a new problem. Hospital. IV solutions need to have a certain concentration for their either dietary or their medicinal IV solutions in order to treat someone properly. You mess that up, you can make them sick. So stoichiometry will allow us to determine yields and limiting reagents just like we did before. The only difference is that we are dealing with concentration, the units are moles per liter, and volume in liters rather than mass in grams and molar mass. So we're going to run through 4 different examples. The first 2 are not reactions, it's just a review of how to do. The first one is a dilution, and the second one is you're mixing 2 solutions, different concentrations, different volumes, but the substance is the same. So how that affects concentration. Okay, number 1. If 100 milliliters of a 2 mole per liter solution is diluted to 1 liter, what's the new concentration? This is a case of dilution, and if you remember, the number of moles of our solute don't change because we're only adding water. So C1V1 equals C2V2. So our volume here is volume 1. Here is our concentration 1. And then this is our second volume. It doesn't really matter which ones you say are situation 1, situation 2, as long as the concentration and the volume go correctly together. So you pick 100 milliliters of the 2 mole per liter, not 1 liter of the 2 mole per liter. Okay, change your volume, 2 liters. So that's 0.1 liter formula, or we could do dimensional analysis. New concentration, we want moles per liter. So we're going to start with a quantity with moles per liter. Now, from that, we took 0.1 liters. We have to use the correct volume here. See, whichever liters you took, you're going to use. And then we diluted it to 1 liter. So these liters cancel, but we need liters again, so we divide by the second volume. So our new concentration is 2 times 0.1 divided by 1. So 0.2 moles per liter. If this is too confusing, then just plug in the values into the equation. Alright, 20 milliliters of 0.1 molar sodium chloride is mixed with 50 milliliters of 0.2 molar solution. Same stuff, sodium chloride. What's the new concentration of sodium chloride? Well, we've technically dissolved, we've diluted our sodium chloride solutions, but we have changed the number of moles, so we can't use the dilution equation here. But what we do need to do is figure out what our total number of moles is and our total volume is. Change your volume to liters. So we can find how many moles we have, and we're going to add those together. So we want moles, and we're going to multiply that by our volume to get rid of the liters. And then for the second one, so we have a total of 0.002 plus 0.01, so 0.012 moles. So that's our total number of moles. Our total volume is 50 plus 20, so 70 milliliters. So we want moles per liter, so we take our moles, divide by our liters, and we get 0.17 moles per liter. So that is our new concentration. And that makes sense that we start with a small quantity of 0.1 and we add a little bit more of 0.2, so it should be somewhere between the two, but closer towards 0.2. So 0.17 mole per liter. Example number 3. Determine the minimum volume of 0.42 mole per liter sodium sulfate. So this is 0.42 moles per liter. That is required to completely react with barium ions in 500 milliliters, so a half a liter of 0.1 mole per liter solution. Okay, so this question is not asking for how much precipitate we need. It is strictly asking for how much of a reactant we need. So we're given two pieces of information about barium chloride. one piece of information about sodium sulfate, yet we're asked for a second piece of information about sodium sulfate. So we can find the moles of barium chloride, use mole ratio to convert to sodium sulfate, and now we have two pieces of information, can find the third. So we need volume, so liters of sodium sulfate as our final answer, our final units. So we are going to use whatever has that in its ratio, and that would be the concentration. So 1 liter of sodium sulfate contains 0.42 moles, and we're strictly taking the concentration here. So we want to get rid of moles of sodium sulfate. So we need the mole ratio. 1 mole of sodium sulfate for every 1 mole of barium chloride. So moles cancel. Now we've got to get rid of moles of barium chloride because we don't want that in our final answer. We have the concentration that has moles. And it's over 1 liter. So moles of barium chloride disappear, and we're left with liters of barium chloride. Don't want that either. So if we multiply it by the liters of barium chloride, that will disappear also, those units. So take everything on the top, 0.1 times 0.5, and divide it by everything on the bottom, so 0.42. So this is going to be equal to 0.1190 liters. We can only have 2 significant digits in our final answer because of the concentration of sodium sulfate, and might as well convert this to milliliters. So we would end up, multiply that by 1,000, so 119, or to 2 sig figs, 120 milliliters of sodium sulfate. So we would need 120 milliliters of 0.42 mole per liter sodium sulfate to completely react with half a liter of 0.1 mole per liter barium chloride in this reaction. Okay, predict the mass of precipitate expected when 1.5 liters of 0.8 mole per liter sodium sulfide, so 1.5 liters, 0.8 mole per liter. We have 850, so show the conversion of that, 0.850 liters, and 1 mole per liter. And we want to figure out the mass of precipitate. So aluminum sulfide is our solid product. So 2 aluminums and 3 sulfurs, and we get our molar mass. So this is 150.14. Okay, so we know what the molar mass is of our product, so we want grams of aluminum sulfide in our final units, and we have to do it from both sodium sulfide and aluminum chloride. Whichever one gives us the smallest mass will come from the limiting reagent. That gets all used up, so that mass will be the maximum mass. So 150.14 grams of aluminum sulfide for every 1 mole of aluminum sulfide. So now we convert aluminum sulfide to sodium sulfide. So that's a ratio of 1 to 3. So now we have to get rid of moles of sodium sulfide. We do that with our concentration. We've got 0.8 moles of sodium sulfide over 1 liter. So we get rid of moles and sodium sulfide. And now we want to get rid of liters sodium sulfide, so multiply it by the liters. And we are going to repeat this process with aluminum chloride. So 150.14 grams per 1 mole. Mole ratio, want to get rid of aluminum sulfide, so it goes on top. Aluminum chloride goes on the bottom. Now we want to get rid of moles of aluminum chloride. There's 1 mole of aluminum chloride for every 1 liter of aluminum chloride. That's from the concentration. And now I'm stuck with liters of aluminum chloride, so I need to multiply that by the liters. So they now cancel. So I'm only left with grams of aluminum sulfide. So let's figure out what these numbers are. So for this last line, this aluminum chloride, 150.14. Ooh, I forgot to do my mole ratio there. 2 aluminum chlorides. Divide by 2 times by 0.85. So this is equal to 63.81 grams, whereas the top one, so 150.14 times 0.8 times 1.5 divided by 3 is 60. So 60 grams is lower than 63.81. So the maximum mass of precipitate is 60 grams, and our sodium sulfide is the limiting reagent. So you can still do percent yields, theoretical yields, if you start with solutions. So hopefully this gives you some insight into how to do calculations.